Now let's talk about AND gate, OR gate, and NOT gate for now. The way we draw a picture of an AND gate, it's a 2-input, could be a 3-input AND gate that applies to as many inputs. It will look like this. That's a 2-input AND gate. If it's a 3-input AND gate, it will look like this. If it's a 4-input AND gate, it will look like this. Has 4 inputs and 1 output. An OR gate, a 2-input OR gate, will look like this. Notice the difference. This end here is curved. See that? This is a straight line. That's a 2-input OR gate. This is a 3-input OR gate. That's a 4-input OR gate. We have these in the lab. Then we have the NOT gate. In the NOT gate, it looks like this. So, how do they work? We'll start with the NOT gate. I'll give you the truth table for it. We'll call this the input. We'll call this the output for the NOT gate. If your input is 0, what's not 0? 1. If your input is 1, what's not 1? 0. So it does the complement. It changes the 0 to 1, 1 to 0. In digital logic, by the way, there's no 0, 1. It's really 5 volts and ground. 0 voltage and 5 volts. 5 volts is 1, or 10 volts is 1. 0 is 0 voltage, or low value. But it converts from low to high or high to low, from 0 to 1, 1 to 0. Now an OR gate, let's deal with 2 input for now. We have 2 inputs. We'll call them A and B, and there's your output. Remember, it's an OR operation. When we say X is less than or equal to Y. So for example, is 4 less than or equal to 5? Is that true? Why? Is 4 equals to 5? No, it's less than. So with an OR operation, you only have to satisfy one of the conditions to be true. Only one has to be true. Is 5 less than or equal to 5? Yes, because it's equal to. So with an OR operation, as long as one of them is true, so 0, 0 gives me 0. Once one of them is high, the result is high. So the way we write that, we go A plus B. Plus means really OR gate. Equals out. So we use plus for an OR gate. For a NOT gate, if it's an input A, we go with the NOT, with the line over. That means that's not. That's not A. A and not A. So you see me put a line over to indicate it's not the complement. Now the AND gate, for an AND one, you have to satisfy both conditions. If I said to you, guess what? The only way for you to go to UMass, the only way, if you have an average or GPA, not average, GPA greater than or equal to 2.7 and graduate from us. And so if you have a GPA of 2.8 and you did not complete all the course to graduate from us, can you transfer to UMass? No. Both of these conditions have to be true for the whole thing to be true. So for an AND gate there, for the result to be true, true like 1, both have to be true. So if one of them is false, you're getting a false. So the only time you get a yes, a true statement, if both inputs are true and true. True and true is true.
So one is true and 0 is false?
True and 0? If true and false?
One is true.
1 is true, 0 is false, yes.
All right, thank you.
Yep. And the way we write that, A and B, and like multiplications. Now, if you think about them in terms of math, actually, notice if you think about them in terms of math, multiplication, what's 0 times 0? 0. What's 0 times 1? 0. What's 1 times 0? The only way to get a 1 if it's 1 times 1. So we use the multiplication to indicate that's an AND. What's addition here? What's 0 plus 0? 0. 0 plus 1. 1. 1 plus 0. 1. The only thing is different, 1 plus 1. It's a fat one. But still, like, that's a 1 there. So that's a NOT gate, OR gate, AND gate. The way to think about them, here, the true is a dominant with an OR gate. Because once one of them is yes, true, the whole output is true. Here, the false is the dominant. So for AND, the false is the dominant. Once one of them is false, the whole thing is false. I don't have a way to remember it for you. Oh, I got it. I got it. Something just hit me. For the OR, we said what? Who's the dominant? The true, right? Is there a baseball player that begins with OR and T in it?
No.
David Ortiz. Big Papi. Just think of Ortiz. Ortiz. Or, when you have OR, T is the dominant. Once one of them is T, or true, the whole thing is true. Now false, I don't know. And A-N-F. Fan backward, or not backward. Well, there's, shuffle them around, that's fan, yes. Fna, anf, but the false is the dominant. To it can be like KFC, something like this I can relate to, food, you know. But if we remember Ortiz, we know the T is the dominant with OR, so the other one's going to be the backward. F is the dominant with false. So if you remember that, Ortiz, then you're okay. Now, we also have, so other gates here, and if you think about them, there's plenty more, but just I'll mention a few of them for now. We'll add the rest later. We also have something called NAND gate. And we have one called NOR gate. When you listen to the name NAND, it's really an AND and a NOT put together. But a 2-input NAND gate will look like this, just like an AND gate, but it has a bubble, the picture drawn like this. So that means it's an AND gate with the NOT at the end of it. You do both. You have 2 gates, put them together, that's what an AND gate is. A NOR gate, again, anytime you see a little bubble there, circle, that means a NOT. That's a NOR gate, which is an OR gate, add to it the NOT. That's a NOR gate. So if you look at the truth table for the AND and OR here, this is the AND and OR. So let's look at the NAND. And this is A and B, but it's an AND. It's an AND with the NOT on top of it. That's an AND gate. So it's going to be the complement of this. So take the 0 now, because you're going to knot that 0. When you knot it, what are you going to have? 1, 1, 1. When you knot the 1, you're going to have what? 0. That's what an AND gate is. NAND. NOR gate. An OR gate is A plus B. Put a knot over it, that's a NOR gate. Again, or the dominants or T's. The T is a dominant. So anytime there's a 1 with an OR gate, you get a 1, but now you got to complement that. Complement the 0, that's a 1. Complement the 1, that's a 0, 0, 0. I can tell you, when we go to the lab, I'm always short on NOT gates. I don't have them. We used to have them, they're gone, we break them. I don't have that many NOT gates. So what do I do then? I can take a NAND gate or a NOR gate. That's a NOR gate. And if I tie both inputs together, or take an AND gate, I just made a NOT gate. By tying both inputs together, once you put a 0, you have what? 0, 0 here. For a NOR gate, when you have 0, 0, what's your output? 1. And when you put a 1 here, you have 1 or 1, and not that, you end up with what? 0. You put a 0, you get a 1. You put a 1, you get a 0. Same thing with an AND gate or NAND gate. If you have a 0, if both inputs are 0, what's 0? NAND 0. 1. When I put a 1, what's 1? NAND 1. That's a 0. So that's how I make my NAND gates. Especially if I have a chip that has 4 gates on it, I use 3 and I'm looking for a NOT gate. Why should I use another chip now for one NOT gate when I can steal that from that same chip there? There's an extra gate sitting there. I can just attach both inputs together and make that a NOT gate. Or a lot of times I'm looking for a 3 input OR gates, AND gates, and I don't have them. I do have them, but I have something loose on the table, and I don't want to go look for another one, add another chip to my design. So if I'm looking for a 3 input AND gate, if I don't have one, or OR gate, I can take a 2 input OR gate, go like this, take the result, OR it together with the third one, and now this is equivalent to 3 input OR gate. He said, are you sure? I go, I think so. Can you prove that? Sure I can. Let me get us a ruler here. Come on.
It becomes easier to satisfy for OR gates.
Well, yeah, especially if, again, you'll see in some of the design, you have 2 inputs, 3 inputs, you have some empty chips, because the chip comes with 4 2-input AND gates on it. It comes with 4. If you're using 3 input, you can buy a chip that has 3 of them. If you're getting a 4 input OR gates, the chip has 2 of them on it. So if I'm using one that has 4 2-input OR gates, I only use 2 of them, I still have 2 empty ones. For my next one, let's say I need a 3-input OR gate. Why should I use another chip when this one has still 2 empty ones on it? So I'll go and use that one. But let's watch and see. I'll do it what we call a truth table to see if that really works or not. So since I have 3 inputs, I should use graph paper for this, will make my life easy. I don't know why I'm making it this big either. 1, 2, 3, 4, 5, 6, 7, 8, and I need the label, the header, 9. So this is A, this is B, this is C. If I have a 3-input OR gate, remember or T's, the T is the dominant here. So as long as one of them, so my output here should be, if I do it right, a 3-input OR gate, if I buy one, when my inputs are 0, 0, 0, my result is what? Should be 0. 0, 0, 1 should be a 1. Bless you. T is the dominant. Once one input is 1, the whole thing is 1. 0, 1, 0. 0, 1, 1. 1, 0, 0. 1, 0, 1. 1, 1, 0. And 1, 1, 1. There's all the combinations for 3. How many combinations for 3 inputs? 8. Why 8? What's 2 to the power 3? Remember, each one has 2 options, 0 or 1, probability here. Each one of these input have 2 options, 0 or 1. So A can be 0 or 1, B can be 0 or 1, C can be 0 or 1. That's 2 options. 2 times 2 times 2, there's 8 of them. So there's 8 combinations, 0, 0, 0. That's the 0, the 1, the 2, the 3, the 4, the 5, the 6, the 7. An easier approach to do them, you start with the one on the right. Alternate every one. 0, 1, 0, 1, 0, 1, 0, 1. The next one you're going to do what? 2 zeros, 2 ones, 2 zeros, 2 ones, 2 zeros, 2 ones. The next one, 4 zeros, 4 ones, 4 zeros, 4 ones. The next one, if there's a next one, 8 zeros, 8 ones. The next one, 32 zeros, 32 ones. The next one, 64 zeros, 64 ones. And that's how it goes. That's what my truth table should be for a 3-input OR gate. But if I connect it like this, do I get the same answer? Well, let's see. Let me find A plus B. Notice I'm not paying attention to C now. A plus B, that's an OR gate. Look at A and B. Once one of them is 1, the result is 1. That's the first gate. Now let's take that gate, which is A plus B, and OR it with C. That's this one right here. So this one is A plus B. This one, A plus B plus C. So this is the C, this is the A plus B. Let's look at these 2 columns, do an OR. Once one of them is 1, the result is 1. 0, 1, 1, 1, 1, 1, 1, 1. Does it equal to that? So notice by taking 2 input OR gates, put them together the way I did that, I created a 3-input OR gate. And if you want a 4-input OR gate, using 2-input OR gate, you need 3 of them. You will need, I'll cheat, I'll use graph paper, so I don't have to write. Makes it easier. Where's my graph paper? If I want to create a 4-input OR gate, it will look like this. That's A plus B plus C plus D. That's a 4-input OR gate. If I don't have 4-input OR gates, I can take 2-input OR gates, attach A. This is A, B, C, and D. attach A and B together, take another one, attach C and D together, and OR them together. And that will give me A plus B plus C plus D. That will give me the 4 input OR gates. Now, how many inputs you have? 4. What's 2 to the power of 4? 16, right? There are 16 combinations here. 16. So I'm going to call this one A, B, C, and D. Here we go. Look how quick. 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. How many do I have so far? 1, 2, 4, 6, 8, 10, 12, 14. There's 16. The next one, every 2. 2 zeros, 2 ones. 2 zeros, 2 ones. 2 zeros, 2 ones. 2 zeros, 2 ones. The next group is what? 4? 4 zeros, 4 ones. 4 zeros, 4 ones. And the last one is what? 8 and 8? 8 zeros, 8 ones. If you look at the decimal value for them, that's the 0, the 1, the 2, the 3, the 4, the 5, the 6, the 7, the 8, 9, 10, 11, 12, 13, 14, 15. Now, if this is a 4 input OR gate, I should have a 1 where? I should have a 1 on every one of these except which one? Except the first one. Let's see. Let me find what A plus B is. Let's do this one. That's the A plus B. So A and B right here, the first two. 0, 0, 0, 0. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. That's A plus B. So I know where to stop. I keep looking like, where am I going to stop here? There we go. Let's find C plus D. This is C and this is D, the last 2 columns to cover the first 2. Just look at these 2 columns. 0, 1, it's always a 1. If you have a 1, there's a 1. That's a 0. 1, 1, 1, 0, 1, 1, 1. Where am I now? Here? Yep. Next one is what? 0, 1, 1, 1. Next one, 0, 1, 1, 1. Now take these 2 and OR them together. Now, as I said, it's not really the hard stuff. It's just draw all these pictures. It's time consuming. So let's look at these 2 columns and OR them. 0 or 0. 0. 0 and 1. 1. 1. 1. Now this is 1 and 0. That's a 1. 1 and 1. That's a 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. 1. Isn't that your OR gate? 4 input OR gate? And we can show you the same thing with an AND gate. You can create a 3 input AND gates by using 2 input AND gates. You can create a 4 input AND gate by using 3 2 input AND gates. Now, I want you to think about this. Going to take us to Boolean algebra. So don't think normal math. Think of what we call Boolean algebra. It's called Boolean. Now, if you take A, which is unknown, and OR it with the 0, what will happen? If you take an OR gate and you take one gate, attach it to 0 and the other one to A, what would you have? A. Because if A is 0, you'll get what? 0. If A is 1, you get a 1. So the result of that is A. Just like a normal math. A plus 1. If you take an OR gate and you make one input 1, what are you going to have for an output? 1. Doesn't matter what A is. That will be a value of 1, regardless what A is. 0 or 1, still 1. 1 or 1, still 1. If you take an OR gate and attach A and A not. Sometimes, by the way, our book doesn't use the bar. They go this. That means not. Because it's hard to put the line over it, like graphically. So what's the result of that? Try again.
0.
Try again. 1. It's an OR gate. Why? When this is 1, what's 1 or 0? 1. When this is 0, what's 0 or 1? Still 1.
True. Yeah.
So this is always going to be a 1. If you take an OR gate, you take A and A naught and put them together, that's always a 1. Now let's do the AND. A and 0. An AND gate with one input 0. 0. An AND gate with one input being 1.
A.
That's A. Depends on A. If A is 0, you have a 0. If A is 1, you'll get a 1. A and A naught.
0.
That's a 0. That's an AND gate. One of them 1, one of them 0. What's A plus A? Notice it's called Boolean algebra, not algebra, because A plus A in algebra and math is what? 2A. Not today.
A.
That's an A. If A is 0, what's 0 plus 0? 0. If A is 1, what's 1 plus 1? 1. What's A and A?
A.
That's A. 1 and 1 is 1. 0 and 0 is 0. What about if we have this, a double complement?
That would just be A.
I usually write that double complement, double bar. So pick a value for A, 0 or 1, doesn't matter. If A is 0, once you complement once becomes what? 1, then complement again, it goes back to 0. If A is 1, complement that, that's a 0, complement the 0, that's a 1. So you end up with A. So double complement cancel each other out, basically. You go, what am I going to use that? Trust me. This is actually very important. You'll see it in a minute there. Now, in math, when you have something like this, we use a distributive property, right? That's still true. This is still true. That's what? A times B plus what? A times C. But if you watch the design of that, this is what? That's an OR gate with B and C, or, and the result is what? AND it with A. How many gates am I using here? 2. Right here, this is what? 2 AND gates and the result is what? How many gates we're using? 3. 2 versus 3. It's the same thing. I mean, I know you're going to get a chip that has AND gates. You need to have a chip that has OR gates. You're right. So I'm still using the same number of chips, but I don't have to connect these. That's going to take some time for us to connect them. I got to solder them there, or have somebody do them by hand there. If I can eliminate that, why would I have this? That's time consuming. Here's a big one that I use and you'll use here. Maybe you want to make that like in big writing. Now, what do you think that's equal to? That's A plus BC. Now why? We'll use the FOIL method. Let's FOIL this one. Let's see. What's A and A? What's A and C? AC. What's B and A? AB. And what's B and C? BC. Now the first 3 on the left, what do they have in common? A. If you take an A out, what's left? 1 plus C plus B. This is an OR gate with one input being 1 already. When you have an OR gate with one input being 1, it doesn't matter what C and B going to be. The result is going to be what? 1. So what's A times 1? A plus BC. That's the reason why that's true. Again, where I use that, a lot of times you have a circuit using OR gates, and they go, I don't want you using OR gates. I want you to use AND gates. I can use that equation to switch them to AND gates. Notice the AND here. So that's our rules of Boolean algebra when we get to them shortly. We have to use these rules to simplify an expression. So let's see if we can simplify some expressions. I'll take a few of them. I'll see if we can simplify it. Ready for one? Here we go. W bar X, Y, Z bar plus W, X bar, Y bar, Z bar plus W, X bar, y and z plus w x, y, and z. You're given this expression. In the question here, we need to build this, but can you simplify this? Because right now, if I was to build this on a board, I need four. I need 4 chips on that board just for that one. Why 4? Because these are 4 inputs and gates. You can only have 2 input and gates on one chip. They come 2 on one chip. So there's 2 of them, there's 1 chip. There's 2 of them, there's 1 chip. But there's 4 outputs coming out. You need to order them together. So that's your 3rd chip. Notice if I was to design this, we'll go like this. That's what the design will look.
Should those first ones be and or things?
Oh, these are AND gates. Yes. AND gates, not OR, thank you. And notice I didn't do what? There's something else I left out. What did I leave out? The knots, right? These are AND and that's OR. Not even touch the knot. So you need a chip for the knot to convert the W to W knot, the Z to Z knot, the X to X knot, and connect them all. So there is 1 chip. They come 2 on a chip. So this is 1 chip right here. This is 1 chip. This is 1 chip. And I need the knot for another chip. So 1, 2, 3, 4 chips on that board already. Well, maybe I can do some trig on that. Maybe I can do some Boolean algebra on that. There's no trig here. I'm getting tired. I better drink more coffee. Let's look at the Boolean algebra. Look at the first 2 here. Do you notice anything common to them?
Z.
Besides Z, there's more than Z. Let's see, wait. Did I copy the question right? The first one, W bar, X, Y, Z bar. So make sure I copied the question right. W, X bar, Y bar, Z bar, okay. Now, W, X bar, Y, Z. W, X, Y, Z. Okay. Before I get to the last 2, the first 2, I was blind first. I thought this was W bar here. But even that still won't do it, so let me underline this, take it out. Look at the last group. What do you notice about the last group? They have W, Y, Z common, right? If you factor that out, what's left? X bar plus X. What's X bar plus X? That's my Boolean algebra. Where's my Boolean? What's A plus A bar? 1. See, that's a 1. So X plus X bar is a 1. So this is W, Y, Z. That's an AND times 1, which is W, Y, Z. Let me copy the rest of the problem. Doesn't really matter which one you write first. W, X bar, Y bar, Z bar. W bar, X, Y, Z bar. And I don't see anything else that simplifies here. I can combine. Does anyone see anything? So that's it for this problem. It didn't simplify much.
The z bar for the last two can.
Well, just the z itself won't help us because you can't simplify the rest of them. Yeah. So that didn't help me much. Let me take another one. See if I can simplify it. I simplified, but it wasn't a lot there. So this is done. Let me try this one. X bar y z bar plus x bar y z plus x y bar z bar plus x y bar z. Hopefully I didn't write that one before, did I? Nope. Plus x y z.
The last two again have x and z common.
True, but before I do that, notice, see this one here? This works really well with this one. I'm looking at it now because I can factor what? X and y bar. Or I can use them this and this.
But the last one goes for the second one better.
The last one?
Yeah.
What-
X, y, z goes with x bar y, z.
It does work with, it also works with this one. And I can look at this. See this one here? These actually work beautifully together. So I know where you're going with it. This one actually works with any of them, almost. It works with this, it works with this. But if you look at this one alone here, they have in common what? X bar y. And if you factor that out, what's left? Z bar plus z. What's z bar plus z? 1. And now if I group these two, let's look at these two here. As the plus. Look at these two. What do they have in common? Y bar, x, right? These two. So what do you have left? Z bar plus z, which is what? 1. And this one, nobody to play with it. Well, you know what? I can take any one of these and put this. They said this one works well with this one. Is that what you told me?
Yeah.
Well, okay. Since you like that one, let me write it twice. Why? What's a plus a?
A.
Still a. So if you write one term twice, it doesn't change the answer. So now I can take this one with this. I could have just wrote this one twice too. That's fine. So now when I write that, what's left here? YZ x plus x bar. What's x plus x bar? 1. And that's my answer. This will fit on one chip because there's 3 2-input AND gates. Before I have, there's one chip, 2 chips and OR chip. The one thing I forgot to add to the list of Boolean actually here, I'll make it in bold. Again, I use that a lot. That one. And the other one, A well, because if you distribute that one, what's A and A bar? A bar, you're multiplying. A and A bar. 1 and 0. Bless you. 0 plus A times B. That's why it's AB. Now to prove this, I gotta play with it. It's not straightforward. I can prove that.
The list to the left of it right there, A times A bar equals 0.
Yes. So, because if you distribute that, it goes A times A bar, which is a 0, plus A times B, which is a B. But to prove this one here, it's a little bit different. We can prove with a truth table, or I can do the math on it, but I use that one actually. So have that sheet handy, by the way. We're going to need it. You'll see that next time. I can do with a truth table to prove it, or I can play games with it. I'm trying to prove that's equal to A plus B. To me, that's equal to A plus A bar times what? A plus B. That's really what that is, because if you do distributive law, what's A times A? A, that's AB that's AB. Next one, what's A bar and A? 0. And this is what? A bar B, right? So I can rewrite that A plus A bar plus A bar B. Now let's look at these two. What do they have in common? B. If you factor B out, what do you have left? A plus A bar. What is A plus A bar? 1. So you can write that A plus B. If you don't like the way I proved it, no big deal. You can do with the truth table. 0, 0, 0, 1, 1, 0, 1, 1. What's A bar? That's 1, 1, 0, 0, right? What is A bar B? This is A bar and this is B. Let's find the AND. 0 and 1, 0, 1, 1, 1, 0, 0, 0, 1 and 0, 0. What is A plus A bar B? This is A bar B, this column. This is A, this column. What is 0 plus 0? 0. What's 0 plus 1? 1. What's 1 plus 0? 1. What's 1 plus 0? 1. And now let's do A plus B. This is A and B. 0, 1, 1, 1. Look at these two. Are they the same? They are the same. A plus A bar B is the same as A plus B. I just said I use them all the time. I'm not done with this section, but we can do a few problems on homework here. Let me stop.